I'm going to get started. Today's announcements are recitation quiz number 3 is next week. And like every recitation quiz, it's going to cover potentially everything up through Friday the week before. So today I'm planning on getting up through ozonolysis and then radical HBr addition. So pretty much all the reactions from this chapter and last chapter of Fair Game except for polymerization, which I probably won't cover. Okay. And then if you submitted an exam for a regrade, you can pick it up from me after lecture today, or you can pick it up at your next recitation, because after today I'm just giving them back to the TAs. Okay, any questions about those two things? Yeah?
Can we get a recitation quizzes regraded? Because we looked at the quiz and there's like a clear, they just didn't understand, I don't know.
Yeah, so yes, go through your TA, and I'm going to apply the same 1 week after it's handed back to you guys window, if that works. So I guess you guys would have gotten them back this week, right? So maybe just either email your TA and say, hey, can I submit a regrade? Or say, hey, I'm going to submit a regrade next week. Or you can meet up with them earlier than your next recitation, if that works. So yeah, I guess I don't have an explicit written policy for that in the syllabus, but that's a good question. So yeah, welcome. Okay, other questions about administrative stuff before we dive right back into it? Okay, cool. Okay, so still in chapter 5, and we're still looking at alkene addition reactions. So we've covered some so far that have similar patterns but end up producing different results because we're using different reagents. What we covered last time was oxymercuration reduction, and then we covered hydroboration oxidation, so a couple of two-part reactions. But so far, everything in this chapter and in chapter 4 has been just simple addition mechanisms. So the first one we're going to look at today, ozonolysis, is really the weirdo reaction from this chapter. It's the only reaction that we're going to see in this chapter that goes further than just breaking the pi bond. So it breaks both the pi and the sigma bonds of the alkene. Okay, so there's two different ways this reaction can go. And like the previous couple of reactions that we covered, this is also a two-part mechanism. But we got a couple different choices of how to do step 2 on this reaction. So it's a two-step reaction, I should say. Okay, so one option uses what's abbreviated as DMS, which is short for dimethyl sulfide. Or, in other words, it's a sulfur with two methyl groups attached to it. So this is basically like an ether equivalent, only instead of an oxygen, it's got the next atom down the periodic table, a sulfur atom. We'll spend a little bit of time at the end of the semester looking at sulfur, but not a whole lot. So what this does is okay, so I'm going to start with the same example alkene that I've been using for some of these reactions so far. What we're going to do is a two-step reaction, step 1, step 2. Step 1 is just straight up ozone itself. So if you remember the formula for ozone, it's O3, it's 3 oxygen atoms. In practice, you can actually generate ozone in the lab by running a strong electrical current through air. And so there are these ozone generators that you can set up and bubble the gas through the reaction. It's kind of stinky, I guess, because ozone is also a pollutant. Okay, and then step 2 is, in this case, we're using DMS. Okay, so the way you want to look at the overall outcome of this effect take the double bond, chop it right in half. You can just like straight up draw a little, I'm going to talk a little bit later on about that disconnect line, but it's basically like a little cut here. Like you may as well draw a little scissors icon that says like break both of those bonds. And what we're going to do instead is we're going to add a double bond to oxygen to replace the double bond to carbon that was lost on each of these carbons. So we're going to get a double bond oxygen here and a double bond to oxygen there. And this looks kind of weird, so, and sometimes helpful if you're having a hard time seeing what's going on there. Maybe draw the H's in explicitly, and that might make it a little bit more visually obvious what you've done. So like that. Okay, so that's one example. Cut the double bond in half, add a new double bond to O here, a new double bond to O here. If we're doing it on a ring, it's still the same thing, but it has sort of an unintended side consequence, and that is if you cut this pi bond that's part of the ring, the pi and the sigma bond together, what you're doing is actually breaking part of the ring open, so you're doing sort of turning this from a cyclic molecule into a linear molecule now. So again, easiest way to draw it is probably just redraw the entire molecule if you want, like even just the entire starting molecule, and then just like erase that bit out of the middle, squeeze an oxygen in there, squeeze an oxygen in there. Looks a little weird. Or you can take this, maybe I'll add that H just for clarity. You can take this thing that's no longer in a ring and you can just unfold it to a linear shape. So you could redraw this as, let's say 1, 2, 3, 4, 5, 6, 7 carbons. Gives you 1, 2, 3, 4, 5, 6, 7. And as always, if we're making or breaking rings, it really, really helps to number your carbons or keep track of them some way, just so you're not accidentally adding or losing one somewhere. Okay, so on our chain, 2 has a carbonyl, 3's got nothing, 4, 5, 6 got nothing, and then 7, I have the other carbonyl and an H. Okay. So as far as the outcome of this reaction, really it's just sort of making sure that you're doing like the right steps. It's straight up changing the connectivity of the molecule. Like this carbon no longer has any association with this carbon that it was double bonded to. And so as long as you can keep track of connectivity, you should be fine. Okay, Okay, okay. Okay, so any other questions about this option for the reaction? Cool. Okay, so the other option, wow. is instead of using DMS, what you can actually do is use water. And you can also add hydrogen peroxide. It's not required, but it speeds things up. Okay. Because hydrogen peroxide is usually like, you can't buy like pure hydrogen peroxide. It's usually hydrogen peroxide in aqueous solution. Sometimes people will just write H2O2 on the arrow because it's kind of assumed that it's going to be added in water anyway. But you might see either one or both of these on the arrow. Okay, so same results as above, but for each carbonyl, if you have H's attached directly to the base of the carbonyl, the carbon, you can replace one H with one OH. and limit 1 per carbonyl. So if something has 2 H's attached to the base of the carbonyl, you're only going to do it once. Okay. So in other words, if we take these same 2 example molecules again, and now we're going to do step 1, ozone still, and step 2, H2O and H2O2. You pretty much want to start out drawing it exactly the same as we did before. Da, da, da. And I'm about to erase part of this and change it. I'm just doing this as like a starting point for me. Okay, so I start out doing the same products I did before, cut the double bond, wedge a couple oxygens in there, and then I'm going to replace 1 H with 1 OH per carbonyl, and it's got to be attached right at the base of the carbonyl. Sometimes you see people who try to replace an H further away if there's nothing right here, but you can't do that. It's got to be right there. Okay, so that's kind of the difference. I guess if you look at what functional groups we're making, up here we pretty much have to make either an aldehyde or a ketone for DMS. Every product that we have is going to have a carbonyl with just some combination of R's and H's coming off of it. Here we're actually more likely to make carboxylic acids out of it instead. Uh-huh.
So do you replace with an OH on each carbonyl?
Yep, so limit 1 per carbonyl. So this carbonyl gets to replace one of its H's with OH's, if it has any, which it does. And this carbonyl also gets to replace one of its H's with OH's. Mm-hmm. Okay, other questions about that so far? Yeah? Yeah, so unlike previous years where I did cover the mechanism for ozonolysis, I'm going to sort of skip it this year just because it's really unnecessarily complicated compared to the stuff that we've covered so far, and I think it just like scares and bewilders people a lot. So if you're interested, it is in your textbook, but it's multiple different steps, and it's sort of, there's a lot there. Good question. So if you're using DMS, it actually goes off bonded to the sulfur. It turns out forming an SO double bond is kind of a driving force for this reaction. If you're using H2O2, I think if you end up needing to get rid of an oxygen, which you may or may not do depending on what's going on with your final products, I think it ends up going off with the water molecule and making hydrogen peroxide, but I may be wrong about that. Okay. Yeah, question.
I noticed in sampling a lot of the questions asked to like include all the products, all their inorganic products. The testing wants to include those?
No, so usually I generally only care about the organic products. Yeah, sometimes in sampling they'll ask like just so we're clear like what else is happening to all the waste atoms that we're not incorporating into the product here, but generally it's kind of less of a big deal than what are we doing with the organic molecule we care about. Okay, so let me do the other example of this one, again using this cyclic compounds. So again, we take this first O3 and then water with or without peroxides. I'll just write them up for uniformity there. Okay, and again, we want to take our ring compound, maybe even just like redraw it to start out, get a couple O's in there, maybe draw our H's because that makes it easier to keep track. And then I'm going to replace the H's with an OH group. And so I'm going to do that down here, replace that H with an OH. Can I do it up here on the upper carbonyl? Correct, yeah, I cannot do it because there's no H's attached to the base of this carbonyl. So this one, this carbonyl up here, doesn't care whether we use DMS or H2O, it's going to end up the same either way. Okay, so if I redraw this, I'm going to get so pretty much the same thing as I did before, only it's got carboxylic acid instead of aldehyde out at one end. Okay, so again, not going to cover the mechanism for this. It is pretty cool and interesting if you want to go in and have a look at it just to see what's going on, but in the interest of covering stuff that is more fair game for testing. I think I'm going to go ahead and move on to the next reaction. Okay, so other questions? Okay, cool. So, so I guess this reaction is kind of weird for this chapter because it breaks the sigma and pi bonds. The next reaction that we're going to cover is kind of weird for this chapter because it's the first time we're going to see single electron movements. So free radical HBr addition. Okay, so free radical is pretty much synonymous with single electron moving around unpaired. Okay. So let me actually do the overall reaction first, and then we can look at what's going on for the mechanism. So this reaction adds an H and a Br, just like regular HBr addition did back in chapter 4. But unlike regular HBr addition, when we start using free radical chemistry, this one actually forces it to go anti-Markovnikov. Okay, so the way we make this happen is what's called a radical initiator. This is responsible for creating those unpaired electrons in the first place, or creating species that have unpaired electrons on them. The most common one that we're going to use is a dialkyl peroxide. Or ROOR. Okay. And one other thing that's worth pointing out before I get into the overall effect is that this specifically only works for bromine, not any of the other halogens. And again, that pretty much just comes down to the way the thermodynamics work out. Only turns out to be favorable. Like bromine's kind of in a sweet spot energetically, and the others are either not energetic enough or too energetic and end up giving the wrong kind of outcome for this reaction. Okay. So let's switch the camera. Overall reaction is going to look like, so HBr and ROOR. And note that unlike the last few reactions we covered, this is not a two-step mechanism. You're just throwing it all in at once, HBr and ROOR at the same time, which means that we don't use one parenthesis, two parenthesis. We could just write it like all on top of the arrow or all under the arrow or wherever. So it's just a one-step deal. And then what we do is we break the pi bond and we add an H to the less substituted carbon, add an H to the more substituted carbon and a Br to the less. So it's anti-Markovnikov. Okay, and again, this guy, we're going to do HBr, ROR, and add an H there, and a Br there. Okay, so that's kind of what we're accomplishing overall. Any questions about this stuff so far before I get into the mechanism? Okay, awesome. So the mechanism for this one is real weird compared to what we've seen before. So let me talk about it some more before we actually get into the details. So free radicals. Remember that the way to show that a single arrow, a single electron is moving is with a fishhook arrow. So if we have for example, so here's two different things, and I'm going to explain why the difference exists between them. So what we've seen so far is generally when a bond breaks, both the electrons out of that bond go to the same place. So normally we'd see this full-headed regular arrow showing both the electrons out of here go to the oxygen. So another way to describe this is what's called heterolytic, which means that, so heterolytic means different breaking. And so that's saying that out of the two atoms of this bond, when the bond breaks, they get different numbers of electrons out of it. One gets both, one gets nothing. What we're going to see here for the first time is something where instead of one atom getting both and one getting nothing, we're going to take a single electron, dump it onto one oxygen, and then also a single electron, dump it onto the other oxygen. All right, so given that they're both getting the same number of electrons out of that bond as each other now, this is called homolytic bond cleavage, or same breaking. So this is where you show the fishhooks, and this is basically the way that you create single unpaired electrons. They sort of rip on that bond until it tears apart, and they each end up with just a single unmatched electron. Okay, so how do we know how to predict which of these things is going to happen? A real common way that this shows up is when you've got two electronegative atoms bonded to each other. So in a future chapter, we're going to see this happening between two halogen atoms, neither of which wants to give up the electrons entirely and take on a positive charge. Here we're seeing it between two oxygen atoms, neither of which wants to give up the electrons and take on a positive charge. So it's real common when you've got like O bonded to O or halogen bonded to halogen that they're going to just rip the bond in half like that. Another thing that you can do to promote this is by shining UV light on it. Which is often written as either UV light on the arrow or just light. Or you may see H and then this curly V sort of written on the arrow. That's a nu. H nu is the equation for the energy of a photon. I don't know why that became the convention for indicating light on the arrow, but you may see that show up too. Probably not for this particular reaction, but we will see it for the other radical one that we'll see in future. Yeah, question? When you say two electronegative atoms, do they have to have the same electronegativity? Good question. It's more likely the closer in electronegativity they are, just because like, you know, the more imbalanced they get, the more likely it is that the less electronegative one's just going to like lose its grip on both electrons. Okay. So one last thing about radical initiators here is another example is AIBN. And I don't remember if I include that in the notes. Oh yeah, here it is. Okay, so I'm skipping ahead a little bit to the end of this section, but may as well cover it while I'm here. So this one, rather than breaking a bond between two electronegative atoms, is actually going to break this bond between the carbon and the nitrogen. And the reason this is like even remotely favorable at all is because nitrogen really, really wants to be triple bonded to nitrogen. If you know anything about like nitrogen fixing or I guess industrial creation of fertilizers, like getting the nitrogen back out of its triple bonded form that it's in the atmosphere takes a ton of energy. And so like giving the nitrogens a chance to go off together is going to be a way to force radicals to get created. So after that happens, you end up with the two nitrogens triple bonded. Oh, I guess I didn't show the dot example up here. Doubling back just a little bit, once you do this, what you're going to get is an unpaired electron on each oxygen, which we show as oxygen with a big obvious dot right next to it. So you could call this the OR radical, or OR dot is real common shorthand to describe that. So you can also show the lone pairs, although those are generally not emphasized as much as the one really obvious unpaired electron that's on there. Same thing here, we're showing carbon dot as the radical that got formed. Okay, so that's a little bit about radicals and how to get them. You might see UV light and AIBN pop up in Sapling or in exam archives for other professors, but I tend to stick with just ROOR for this chapter. Or I might, in some cases, use like a specific version of R, so I might say like methyl OO methyl is one example, or tert-butyl OO tert-butyl. Question?
Would you record the charge on this as like a negative 0.5?
So what's the formal charge on this oxygen right now? Given that it has, for itself, it's got 1, 2, 3, 4, 5 electrons plus a sixth out of the bond, because it gets to count half. So technically, this oxygen is neutral charged, and so is this one. So that's kind of the weird thing about radical chemistry. They're really reactive species because they have an unfilled octet, and they want to fix that. But they don't actually have any pluses or minuses on them, weirdly enough. So yeah, we're going to see them start reacting in just a second here. Any other questions about this first, though? Yeah.
Is it incorrect to show the half arrows coming from either side of the nitrogen, going to the nitrogen as you go to the bond?
Yeah, I guess if you showed it going onto the nitrogen, then what you're implying is that you're going to end up with a dot on nitrogen. And like immediately if that formed, it would just throw its electron into a triple bond instead. But I think like showing this implies that it's actually pausing for some instant of time on the nitrogen, which is just going to bypass that and make the triple bond immediately. So yeah. Okay, cool. So let's start doing this mechanism. The mechanism actually has 3 kinds of steps. So for radical reactions, it's actually a chain reaction where you make some radicals to start out with, then the radicals do some stuff to the molecule, and they can do that over and over and over and over and over, some like hundreds of thousands of times. And then eventually something happens and the radicals die or get killed off. So we're going to look at initiation, propagation, termination. Okay, so radical reactions, you want to think initiation, propagation, termination. Okay, so initiation first. Here's where we're going to make the radicals that are actually going to react with our molecule. So we already know that we're going to get this reaction kicked off by our ROOR splitting up like that to make a couple of OR dots. And then what's going to happen, and you can either show this continuing on from here or do it as a separate line. A lot of the time for radical reactions, people kind of like having each step be on its own separate line just to sort of keep track of things a little bit easier. Okay, so initiation, note that at least one initiation step involves creating two radicals out of no radicals. So you had like all filled octets over here, and then once you split these up, this is where you're actually making your two radicals. So you're getting radicals at all. Then what we got to do is make sure that we have a radical that's going to be the one that we actually want to react with our molecule. So this is going to be a real common way of like arrow pushing patterns for this reaction. Let me scoot this away just a little further for space. Okay, so this RO dot is going to pull a hydrogen off of this HBr molecule. It's not an acid-base reaction because it's not coming in with a full pair of electrons and you're not transferring a proton. This hydrogen is actually, if it wants to make a new bond, it's going to have to bring one electron with it. So it's not a proton and it's not a hydride either. It's a hydrogen with one electron. So oxygen is going to chip in one electron to make that new bond. And you can show that sort of going into somewhere in the space between the oxygen and the H. Hydrogen shows up bringing the other electron that it stole out of its bond to HBr. And then the leftover electron out of this bond is no longer needed for the hydrogen. It just kind of falls back onto the bromine here. Okay, so you end up with a new bond from the oxygen to the H, and you end up with Br dot now. Okay. So this is making the radical that's going to react with our alkene in just a second here. Okay, so we're good to start the actual reaction that we care about now. We've got everything set up and ready to go. Any questions about the initiation so far? Okay, cool. So let's get into propagation. Okay, so what we're going to do, and I'm going to use the same alkene I used up here for an example, is I'm actually going to do pretty similar arrow pushing to when I did this step here. I have one radical species, one non-radical species. The radical is going to start out creating a bond to something over here, but it can only bring one electron with it. So the other molecule, the non-radical, has to contribute the other electron to making that bond. And then the leftover electron just falls back onto whatever else just lost a bond. Okay, so this same combo of three arrows is pretty much the same deal up here in this step as it is down here. It's just happening to different atoms. Okay, so once that's done, I now have a bromine to carbon bond, and I chose this particular carbon for reasons I'll explain in a second here. And the leftover electron is now on carbon, so we got a carbon dot going on. Okay, so at this point, what's going to happen is this carbon is still not very happy about having an unfilled octet. So now this radical is going to come rip an H off of whatever it can get a hold of, which is most likely going to be HBr. So it's going to do exactly the same set of 3 arrows again. Radical contributes 1 electron to a new bond. Breaking bond over here contributes the other electron, and then the leftover falls back onto the last atom. Okay, so we just made a new CH bond. And we made another Br dot. Okay, so this is the cool thing about propagation. The radical that we started with, that we came in with from initiation, the Br dot, should be the same as the radical that we're spitting out at the end. So we sort of have a Br dot that goes, does something to the molecule, some stuff happens, and then at the end we spit out another Br dot that goes, finds another alkene, does the reaction with it, spits out another Br dot, and again and again and again and again. So as soon as you've got your radicals created, they're going to just churn through the alkene and just continually convert it to the anti-Markovnikov product by burning up alkene and HBr. And it should end up creating the same radical that you started with for that thing. It's kind of a closed loop almost, except that you're actually creating product at the same time. Any question?
Is this the reason why your radicals are so destructive?
Yeah, and so biochemically, we have a lot of ways of sort of trapping these and turning them into something less reactive. And so, yeah, free radicals are having an unfilled octet means they can do a lot of reactive stuff that you wouldn't normally want energetically. Yeah. Okay. So any other questions about this so far? Yeah.
I just wanted to make sure that the Markovnikov rule, usually the hydrogen would want to go to the carbon with more hydrogens on it.
It would, yep. Yeah, so that's actually, here, do you mind if I erase the board over here real quick and then talk about that regioselectivity bit? Okay. So, regiochemistry for this reaction. So why is it anti-Markovnikov? So all the times we saw Markovnikov's rule getting followed before, it always came down to where is the carbocation most stable, like where are you going to best put a positive charge or delta positive on the molecule? because that always wants to be more substituted, and then everything else happens just as a consequence of that. Turns out something real similar is happening here, only instead of a carbocation, it's a carbon radical. So C dot turns out has the same preference to be more substituted, or as substituted as possible. That carbocations have. It turns out it's not as strong a preference. So like carbocations want to be substituted so badly that they're actually going to rearrange if they have to. Carbon radicals won't rearrange, but they still like being substituted. Okay, so when I did this step over here where I added Br dot, I could have made either the one that I did make, where it's got the carbon dot there, or I could have made this one here with the carbon dot out on the outer carbon. Given that carbon radicals like to be more substituted though, this one is the better choice for stability, which is why it ends up on this carbon, which is why ultimately you end up doing anti-Markovnikov addition. So pretty much it just comes down to always where is the carbon going to be happiest when it's at like the high energy stage, the radical or the carbocation during the reaction. Uh-huh. Good question. So yeah, it's always going to be the major product. The more stable one is better. So this is always going to give the major product, and this one gives the minor product. So you are, like pretty much every reaction that we've done for the last couple chapters now, even though we say like Markovnikov style, that just means that the more substituted product, or the group with the not an H on the more substituted carbon is favored, but you're always going to get a little bit of the wrong one mixed in with it. So Markovnikov addition will always give you a little bit of the anti-Markovnikov mixed in, and then anti-Markovnikov will always give you a little bit of the Markovnikov product mixed in. But we pretty much only show the major product. We're assuming whatever the other crap in there is getting cleared out by like recrystallization or workup or whatever.
Okay, just a follow-up to that. Do we talk about the K and Q for like both of those products at all?
You can, I guess, I don't know if people tend to dig that much into the level of detail unless they're really doing an in-depth like kinetic study on the reaction. Usually it's more like, hey, we ran this reaction, we got like 90% of the one we want and like 5% of the one we don't want plus some other stuff, and then we just got 90% yield is how we'll label it. Yep. Okay. Cool. So other questions about this before we finish up this reaction mechanism? How much time I got left? Oh, okay. Cool. I got 2 minutes. All right. So the third part of this, termination. Okay. So statistically, you only have a small number of radicals present at any time. Like the concentration of OR dot or BR dot or C dot is tiny compared to all the other stuff in there that's not a radical. But once in a while, you do have the odds that two radicals are going to bump into each other. So two radicals can join together and kill each other off. So this is pretty much the only way to fix an unpaired electron, is to pair it up with another unpaired electron. And it can be any two radicals getting together. So Br dot and say OR dot could get together. It's statistically unlikely because there's not that much of either one of them around at any time, but this is a possible termination step. Or we could have a C dot bump into a Br dot, for example. pair up our electrons that way. So we are, in addition to the Markovnikov and the anti-Markovnikov product, we're going to get a little bit of this dihalogenation product, weirdly enough. And then, weirdest of all, and often most complicated to draw, we can have, and I'm going to have to flip this one upside down, 2 copies of C dot get together and stick together. So we're going to get at least some fraction of our product that ends up being this what's called a dimerized product. Or a dimer for short. We'll talk a little bit more about where that name comes from in the next lecture, because it's related to polymers. Okay, so that seems like a good stopping point. Any other questions about this? Okay, cool. Have a good weekend. If you submitted an exam regrade, I got them up here. Other than that, I'll wrap up the chapter on Monday.